Okay, good afternoon. Short class today. Um, few announcements. The first one is about the homework. There are several issues with the homework. It's been very frustrating for the students. It's also been very frustrating to me. I didn't realize this chapter was like so full of errors. Anyway, so I think each and every problem in there had some sort of minor glitches or errors. Their circuit diagram was not correct, or the system was not taking the answer instead of amps, it was taking in milliamps. Anyway, so I've gone through most of the problems over the weekend. I'm going to rearrange a few things in there. So either I'll drop the homework problem or I would convert it into extra credit or something. I don't know. So especially the ones where it's obvious that there was an error in there. So again, I apologize. I wasn't aware of these errors and these problems before assigning. Okay, so that's for the homework. Quiz will be most likely on Wednesday, not on Monday. I'll be on logic gates, last remaining topic, and then final exam. Friday will be like open, so like no class. I'll just review everything on Wednesday. And final exam page is already updated. Saturday is the first available option for students to take the final. Some students have signed up to take the final on Saturday, so you know, Monday and Friday students can get their questions answered. But for the most part, we are pretty much through everything that I wanted to cover. So we'll go into a few other smaller topics today. Not this. This. All right, so we looked at the CMOS transmission gate made up of two MOSFET devices, one PMOS, one NMOS. There's a control voltage, VC and VC bar, to turn on both devices at the same time or turn off both devices at the same time. And there's a V in and a V out, input and output. This is a bidirectional transmission gate because the input can be taken, the input can be given at either terminal and the output can also be taken at either terminal. However, actually, before we get there, just want to do a small SPICE simulation for a transmission gate. Here is the logic inverter. What happened? Inverter for control voltage. Okay, inverter for control voltage. And this one is the transmission gate. Okay, so V in, and then this would be V out in the black drawings. Transmission gate, obviously, the inverter gate obviously simply inverts the input given to it. So if you give 1, output is 0. If you give 0, output is 1. The transmission gate, however, is going to hold the input until and unless the control voltage is active. So when the control voltage is active, whatever is available at the input is sent to the output. So in this case, we are wrapping the input V1 up from 0 to 5 volts and back down to 0. And you're applying a rectangular pulse waveform as the input of the control inverter. So when the input arrives, turns on the transmission gate, we obtain the output. And when it's off, 0 output. So it tracks the circuit tracks the input coming to the control voltage inputs. Until and unless the control voltage is active, transmission gate is not going to permit the output to go output. Sorry, let me back up. Until and unless the control voltage is active, the transistors do not turn on Hence, the transmission gate does not transmit the input to the output. Okay, input is a simple ramp that we are providing, which is shown here in blue. And so we obtain this kind of output waveform. Okay. Transmission gates can be used as both analog as well as digital gates. It can transmit analog signals. It can also transmit digital signals. So what we saw was just an example of both analog as well as digital. Okay. Buffering. In logic circuits are created with multiple blocks. Okay, so logic circuits are created multiple blocks of logic gates, like controllers. So if you have a counter, it comprises of multiple gates connected in a cascading or a serial fashion. So the output of one gate is fed as input to the next, and the input to the second one fed to the third, and the third to the fourth, and so on and so forth. So oftentimes it happens that the output of the first gate is not sufficient to drive the output of the first gate is not sufficient to drive the input of the second circuit that is connected to the output. And in those cases, we need to isolate the two circuits. One example that we saw in the lab was when some students were trying to drive the LED from a counter or comparator circuit, and the output of this logic gate or the logic circuit may not be sufficient enough to provide the voltage or the current. And if that's not sufficient, then the LED is not going to turn on, or maybe if you're connected to the motor is not going to turn on, the solenoid is not going to turn on. So LEDs, let's take the simplest example, like an LED. LED requires at least 1.1 to 1.2 volts to turn on, requires about 15 to 16 milliamps of current. So if either the voltage is lower or if the current is lower, the LED is not going to turn on. And so what we do is we place a buffer circuit. And let me make this a little easier. We place a buffer circuit in the middle. The sole purpose of the buffer circuit is to take the input signal, take the output signal from circuit 1 and provide it as input to circuit 2. The power to do so is supplied separately. Okay, it's supplied separately. So in case, let's say circuit 1 is sending a certain output, we need to increase the current of that output. Then we connect the isolation buffer. The current to drive that output comes from VDD plus VDD or minus VDD, as the system may be, and then it's fed into circuit 2. One of the most common ones you might have come across or used is basically the voltage follower circuit created using an op amp. And so, if you all remember, perhaps the circuit. This is the voltage follower circuit built using an op amp, where the output of the op amp is fed back as input into the inverting terminal of the op amp. Output of circuit 1 or the input is simply given to the non-inverting terminal, and V out follows V in. And so V out is equal to V in, hence known as a voltage follower. And this is also known as a isolation buffer. And so any kind of input can be given to the circuit, but the power that is supplied at the output comes from the power rails. Okay, it comes from the power rails. So in this kind of logic circuit, let's say you have a standard 2-input NAND gate or NOR gate, or even a NOT gate. You have 2 or 4 transistors. Excuse me. I mean, not NAND or NOR. Any kind of logic gate. What we can do is we can connect a circuit comprising of 2 inverters connected in series. These 2 inverters connected in series form what is known as a logic buffer circuit. A logic buffer circuit. What this does is it actually increases the output resistance. Okay. Sorry, not increase. Fixes the output resistance. If you take a logic gate, let's say a 2-input NAND gate, okay, 2-input NAND gate, and you're going to connect the inputs like 0, 0, 0, 1, 1, 0, or 1, 1. Well, when both inputs are connected to, well, either input is like 0, 1, or 1, 0, then the output resistance is fixed, it's determined, it does not vary. But when both inputs are connected to ground, as seen in the circuit, then the 2 resistors of the 2 MOSFET devices are attached in parallel. And when that happens, the output resistance is actually changing. We don't want that output resistance to change. Okay, it changes depending on the state. So that is not desirable. When that changes, the output current changes. And so that's not, again, that's not something, that's not desirable. Okay. And so if we create a buffer between the output of this logic gate and the next circuit, then the output of the buffer gate is going to have a fixed resistance. It is not going to vary depending on the state of the input. So we have looked at the basic NOT gate, NAND gate, and the NOR gate. Each of these requires at least 2 or 4 transistors. So if you want to attach a simple logic buffer circuit, as shown in the circuit here, this logic buffer comprises of 2 inverters, and each of these inverters require 2 transistors. Okay, each of these require 2 transistors. So if you want to add a buffer to each of these gates, well, then you have to add 4 more transistors at a minimum. And so a 2-input NOT gate, a 2-transistor NOT gate becomes a 6-transistor buffered NOT gate, or a 10-transistor, depending on how many buffers we wish to connect at the output. So while we're implementing a solution, there's always a trade-off. The more gates we connect, the longer it takes for the signal to propagate through the system. So propagation delay is a big concern. Input capacitance, output resistance, and drive capability is also a concern. Okay, but propagation delay is the main, and we'll see that in the next slide. This here is unbuffered, and this here is buffered. You can see here the transition between low to high and high to low. There is a slope, right? There's a slope in there for the unbuffered chips and the buffered ones. Sharp transitions. Unbuffered ones, of course, are going to lower your noise margin, right? Because it's at a state which could be, if there's a noise signal that arrives, now your tolerance for the noise margin, noise signal, is now far lower than if the transition is sharp right here at the buffered. Okay, so visually we can see why this kind of switching would be desirable, right? The downside to that is, of course, that the buffered gates are slower, propagation delay. Obviously, the more number of gates you add, the longer it has to go. So unbuffered gates are slightly faster. The noise margins are lower, which of course is higher noise margins would be desirable. And then the resistances are variable. Okay, we don't want that. We don't want our resistance to vary. Okay, oftentimes in digital circuits, when we create logic circuits using these transistors, then sometimes it becomes very cluttery. Okay, so the schematics are simplified by simplifying the symbol for these transistors. So the enhancement mode transistors, you recall, technically correct one would be that the gate is divided or noted in 3 separate pieces, right? Here you can see the gate is one single line. Plus, you have a bubble on one of those transistors. So you have studied digital logic circuits for a while now. What do you think the bubble means? It is a PMOS, but the bubble means it's active low. So bubble indicates active low. If you had a digital chip and you looked at the schematic of the chip and it says active low or with a bubble, well, it needs 0 at that pin to be active. Okay. Absence of a bubble means it's active high, meaning you connect it to VDD. So here, of course, we have a PMOS, NMOS. This is an inverter, and this would be like a transmission gate. Also notice the 4th terminal, which is the bulk or the body or the substrate of the device, is not shown, which again makes it far easier, far less cluttered schematics. They should be cluttered. All right, one special function inverter is the tri-state inverter. So in a tri-state inverter, we add a 3rd terminal known as enable. And all we are doing is connecting the output of an inverter to a transmission gate. So this is the inverter. And so we add a 3rd terminal. And in this terminal, the enable pin functions to control the output of that inverter. Okay. Hence, we call it a tri-state inverter. When enable pin is high, transistors turn on, and the output of the inverter is sent through the transmission gate. Okay. We can also create, as an example of another circuit called positive edge detection circuits. So this kind of circuit is simply comprised of an AND gate. And the output of an AND gate is logic 1 or logic high, only when both inputs are connected to logic high, right? And so if you take an input signal, give it to one input of the AND gate, and you take the same signal and send it via, invert it, and you send it via 2, 3, 4, 5, or even more gates, then you're inserting a delay in that signal. So the same signal now arrives inverted and delayed, fed into the input of an AND gate. And the AND gate, obviously, is only going to give you 1 when both inputs are 1. So positive edge transition is here and here. So the design of the circuit is that whenever a positive edge or rising edge is sent in, the circuit will send a pulse output. And so by inserting a delay in there, now the output, so this is 0, this is 1, this is 1, this is 1. All other times, something or the other is at 0. So you've broken up, due to that delay, you've broken up into 1, 2, 3, 4, 5, 6 different parts. And only the positive going edge transition is where the output going high. Okay. This slide, there was something that I didn't, either there was an error or I didn't fully understand. And so I told students in the previous section, I will revisit this later on and see if I have a better explanation for this slide. For now, I'm going to skip this. Okay, ring oscillator. Ring oscillator is something that we created in the lab. So we had a chip that had 6 transistors on there, connected into an inverter fashion. The output of the first one is fed to the second, second to the third, and third back to the first. So if we start with a 0, then you have a 1, a 0, and a 1, which is fed back to the input, and then the cycle continues. The output switches between 0 and 1, and so it's oscillating between 0 and 5 volts. However, if you remember, the output was not a perfect square wave, right? So if we connect a capacitor to the output right here, you have capacitor charging and discharging, and then we can approximate sort of a sine wave output. So logic gates, this is just like a tiny drop, so to speak, of what we can accomplish with logic gates, right, and circuits. Right? You have studied digital design in your other classes. There are several other classes you take where you can design circuits. But this class is focused on teaching students exactly how these circuits are created. So more towards the fabrication, like real life fabrication, not simply looking at it as a block diagram, but looking at the internals, right? And finally, just wanted to do a brief, very brief blurb about fabrication. So early on in the quarter, I brought in some silicon wafers. I showed students some of the wafers that were built here at Cal Poly. And here's an example of why it is so challenging. This is the typical diameter of a human hair, which is about 50 to 75 microns. And the smallest feature size in this chip is 0.1 micron. 1 micron, as a reminder, is 10 raised to -6 meters. It is 1 millimeter divided into 1,000 parts. And 1 nanometer is 1 micron divided into 1,000 parts. The current state of the art fabrication is 3 nanometers or 4 nanometers. There's only a handful of companies in the world that can do this. TSMC is one of them. Samsung is trying to do it. Intel, I think, is also trying to do it. But this is the current state of the art. We are fast. We have approached the limits of what can be realized, and your engineers are still finding a way to actually push those limits. Anyway, the smallest feature size I actually ever worked with was about 5 to 10 microns. Most academic clean rooms would be in that range. There are specialized facilities in academia where you can go down to the nanometer scale. So students are actually working with feature sizes that are in the nanometer scale. But most academic clean rooms and research is still in the micron scale. Because even though the technology is several decades old, that is still the gold standard. The principles are still the same. Those aren't going to change. Okay. So we're going to end class here today. And then on Monday, it'll be mostly like a Q&A session where students get their questions answered. And Wednesday will be the quiz based on logic gates. All right. And as I said, I'm going to take a look at the homework and I'll adjust the points accordingly. All right. I will bid you all a good day, and I will see you all on